Hello again. I'm going to continue talking about compact discs, and specifically in this video I'm going to show you how the laser reads the information, the data contained on a disc. And just noted from my last video, I spelt compact disc with a K on the end. I've corrected that. Compact disc is spelled with a C on the end. Anyway, so I just want to point out before we move on that this is a cross section of the CD, and we have our label, we have our acrylic protective layer, the aluminium layer that the laser reflects off of, and underneath the foundation to the entire disc itself is this polycarbonate plastic layer, and it makes up a large part of the disc itself. And it's this polycarbonate plastic layer that is clear, and we can see, if we turn a disc over and have a look at the underside, we can see directly through to the aluminium layer that the laser reads. This polycarbonate plastic is quite clear. Now, let me just put a new layer here. Okay. Well, the picture that I have here is an electron micrograph of a CD surface. So if you turn the CD upside down, the read side, the part that the laser reads, if you could focus in, if you could zoom right in, and this is magnification 16,000 times, you would see these bumps. And remember that this is a bump here, bump, and this is land area, or lands. And note these distances. 1.6 micrometers is equal to 1.6 by 10 to the minus 6 meters. So very small indeed. The width of the bumps, half a micrometer. They're calling this pits, and these may in fact be pits. I remember that in the last video that the pits are actually the reverse side of the bump layer. So if you're holding a CD the right way up as you take it out of the case, for instance, if you were to look with an electron micrograph through the label, you would see pits instead of bumps. Flip it over and you see the bumps. So we'll just assume for this video that these are the bumps on the underside. Note also in the last video that the bumps or the land represent a string of zeros, and it's the change between the bump and the land that will record for us a 1. Otherwise we have zeros. Here's a change, turns into a 1, 0, 0, change, 1, 0, 0, 1, etc. So what sort of size are we talking about here? If you, now, what's a good comparison? I have one here. Okay, a fingerprint. Now, if you can imagine a fingerprint on a piece of glass, it's quite thin. In fact, a fingerprint is equal to approximately, I'll just be very specific about that, approximately 15 micrometers thick. So that might put this into perspective. 1.6 micrometers is much smaller than that. And the height of these bumps compared to the land, so how much they stick out coming out of your screen, is approximately 0.1 micrometers. So I'll write that as well. Height of bump approximately equal to 0.1 micrometers. So they are very small indeed. So how does the laser read this? Well, we need to know something about the laser first. The laser is a red laser, but it's an infrared laser. So the light from it we can't see. Laser. And that's approximately also 780 nanometers. That's the wavelength of the laser. Now remember earlier in the video I said that the polycarbonate plastic layer is the medium through which the laser travels in order to read these bumps. We'll know that the speed of light, c, is equal to 3 by 10 to the 8 approximately meters per second. That's the speed of light in a vacuum, or approximately for air. Moving through the polycarbonate plastic layer has a refractive index of 1.55 times slower through the polycarbonate plastic layer, which if you know V equals the frequency multiplied by the wavelength, if we change this, then and the frequency and wavelength are inversely proportional, we actually reduce the wavelength of the laser to approximately 700 nanometers. Oh, sorry, beg your pardon, I've made a mistake. That's the range of our vision. We can see 700 nanometers as a red colour. The approximate, we lose quite a bit of speed, 1.55 times, so much less than that. So we're looking at about 500 nanometers, which is in the green region of the spectrum. So CD lasers can be referred to as green lasers sometimes, and they don't originate as green. They originate as this infrared, and because of the polycarbonate plastic layer, they slow down a little bit. Now, if you looked at the laser and how the laser looked on the bump, it'd be approximately this size. Sorry about my circle. So, and that distance there, straight up and down distance, is approximately 1.7 micrometers. And I should have done that green actually, because when it hits that bump it is green. We can't see that, of course, the CD is shut. So we might leave that there. I'm going to talk about the interference of light and how this laser then, by reflecting off of this surface in a second, how this laser or how the equipment in a CD player reads these bumps and reads the land and can convert it into a digital signal, so that can be deciphered and turned into an analog signal for sound, for instance. Thanks for watching.